Hey everyone, let me briefly introduce forensic toxicology. It is a field that analyzes toxins, drugs, and chemicals in biological samples to help determine cause of death, poisoning, or drug use in legal cases. It is important because it supports overdose, poisoning, and drug-related crime investigation, aiding both prosecution and defense. Techniques like chromatography, spectrometry, and microscopy help detect drugs, including paracetamol, and track emerging substances, making it vital in both justice and public health. So the drug chosen is paracetamol, which is widely used for pain relief and fever reduction, and commonly encountered in forensic toxicology due to its therapeutic and overdose potential. So why paracetamol? Pharmacological profile make it critical for forensic investigation, especially in overdose cases. Forms of paracetamol selected. The first one is soluble form, which is rapid absorption into bloodstream, and the second one is insoluble form, which is slower absorption, affects overdose toxicity. So the forensic technique used is UV spectrophotometry and SEM. So what is our objective? Our objective is compare solubility and its effect on drug distribution, metabolism, and toxicity, and also use forensic techniques to differentiate between the two formulations.
Method session for UVVs. First, we prepare the sample operation. One tablet of soluble and insoluble paracetamol being dissolved in 100 ml of distilled water, then be filtered and diluted in suitable absorbent. For calibration curve, paracetamol standard stock being prepared, which is 1000 mg per liter, standard 5 to 30 mg per liter, and being measured at wavelength 243 nanometer. Then linear calibration curve being plotted, absorbent versus concentration. For concentration determination, sample absorbent being measured at 243 nanometer. Concentration was calculated using calibration equation, and we compare the solubility and drug release of both formulation.
For method section for SEM, the first method is to sample selection and preparation, where the Panadol soluble and regular Panadol is crushed into a fine powder using a mortar and pestle. Next is we send the crushed Panadol into a coating and mounting, where the layer of the outer layer of the Panadol is coated with carbon to improve the electrical conductivity for clear imaging. Next, the third one is the equipment and imaging. The SEM brand is Nova Nano SEM 230 with 15 kilovolt accelerating voltage. The image that it can capture at is 2000 magnification to observe the surface morphology and structural difference between regular Panadol and Panadol soluble. For data analysis on SEM, the feature for Panadol soluble and Panadol regular is the surface texture, whereas the Panadol soluble has a rough, porous, and cracked structure, and the Panadol regular have smooth, compact, and less porous. For the surface density, Panadol soluble has low, loose, and fractured, whereas Panadol regular have high and tightly packed. For the expected dissolution rate, the Panadol soluble has a high and fast disintegration, whereas Panadol regular has low to moderate. For the formula implication, Panadol soluble has rapid drug release in water, and Panadol regular has gradual release in GI tract.
In this analysis, we use UV spectroscopy to determine the concentrations of soluble and insoluble paracetamol. Both forms exhibited a peak at 243 nanometer, which attributed to the aromatic ring structure in the paracetamol molecules. The calibration curves for both samples show differing sensitivities. This is the soluble paracetamol had a gentler slope, which indicating lower sensitivity, while the insoluble form had a steeper slope, suggesting greater sensitivity. The concentration of soluble paracetamol was calculated to be 11.41 microgram per milliliter, while insoluble paracetamol was 16.15 microgram per milliliter. These results reflect the differences in solubility, with insoluble paracetamol absorbing more light. This demonstrates the reliability of UV spectroscopy for the quantifying paracetamol concentration.
In conclusion, SEM and UV-Vis analysis effectively distinguish between soluble and insoluble paracetamol formulations. Soluble GSK show a porous structure with a lower concentration, indicating a faster disintegration. Insoluble paracetamol was denser with a higher concentration, suggesting a slower release. These findings highlight the impact of formulation on drug behavior and support the use of SEM and UV-Vis in forensic toxicology for identifying drug types and potential misuse. That's all from us. Thank you.